Hello friends, I welcome you all on India's largest live e-learning educational platform, that is Gradeup. All the candidates who are joining me, just quickly confirm whether my audio and visual quality, everything is clear so that we can proceed. Yes, Akumi, good evening. How are you? Welcome to the session. All the candidates who are joining me, just quickly confirm whether my audio and visual quality, everything is clear. Tanish, hi. Good evening. Good evening. Welcome to the session. Just quickly confirm whether my audio and visual quality, everything is clear. Now, till you report me this, let me just brief you about the session. In this series of sessions, we are discussing the important expected topics for GATE 2021, and we started this series and we have completed 2 sessions. We have completed 2 lectures we have completed. If you have missed these lectures, then you can watch them. The playlist is available on the Gradeup Gate YouTube channel. Clear? Now these sessions are planned 9 p.m. in the evening, so that even if you are working, you can join the session. Now friends, we have started with the DC machine, and today I am going to discuss speed control of DC motor, and I will try to finish it in 45 minutes. Okay. So all the candidates who are joining me, just quickly like the session, share and subscribe so that maximum people can be benefited out of it. So like, share and subscribe the session. Now let us start with the session. Some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh, and this is my brief profile in front of your screen. Okay, Chander, thank you. Now let us start with the topic that we want to discuss, that is the speed control of DC motor. The first thing you have to understand, that why you want to control the speed. The first question is why? Why you want to control the speed of any motor? Because you want to drive a certain load, and for that particular load there is going to be a desirable speed. You cannot run your motor on any speed. You want a desirable speed of the motor to run a drive by using the motor. You want a desirable speed. The answer is you want the desirable speed, not any speed. And that is the reason you want to control the speed of your motor. Now the question is how you can control the speed of your motor. We have discussed that if you talk about the motor, we will be talking in terms of back EMF, which is given as K phi omega. Now K is a constant, so you can write EB is directly proportional to phi and N. Omega you can write as 2 pi N upon 60. 2 pi 60 are constant. From here you can write N directly proportional to EB upon phi. Now for a motor, in general, for a motor, if you want to write the back EMF in terms of the terminal voltage, then how you can write it? You can write it as V minus IARA upon phi. This equation tells that if you want to control the speed, then what are the different methods you can have? Number 1, field flux control. Number 1, field flux control. Number 2, armature resistance control. Armature resistance control. Number 3, armature voltage control. So basically these 3 methods you are going to use for controlling the speed of your DC motor. Is it clear for everyone? Tell me yes or no. Tell me yes or no. Now if you are going to use your motor, suppose you talk about the constant speed drive. Now very easily you can understand that DC shunt motor is going to be the best choice, because DC shunt motor is almost constant speed. I am not saying it is constant speed, I am writing almost constant speed motor. That is why we are calling it as a constant speed drive. For example, if you draw the characteristic in terms of the speed torque characteristic, then almost the speed is coming constant for the DC shunt motor. So for constant speed drive we are using the DC shunt motor. Now suppose you want to have a constant power drive. Constant power drive. Now you know that power you can write in terms of torque multiplied by the angular speed. If the power is going to be constant, then you can write that speed is going to be inversely proportional to the torque, or you can say speed is going to be inversely proportional to the torque like this, and DC series motor is going to be the best choice. You know the characteristic. This is torque, this is speed, and the characteristic is going to be like this. Everybody just tell me, are you able to follow this or not? Thank you, Amit. Thank you for your appreciation. Now let us see the adjustable speed drive. Let us see the adjustable speed drive. When you talk about the adjustable speed drive, so you want to control the speed control both above and below the rated or base speed. You must be knowing that the rated speed we are generally calling as the base speed, and if you see the variation of the power and torque with respect to speed, either power or torque, then if this is your base speed, suppose this is your rated or base speed, then the curve is going to be like this. Now if you see less than the rated speed, you will be getting a constant torque and variable power drive. That is constant torque and variable power drive. Now you know constant power P is equal to T into omega, constant torque. So if the torque is going to be constant, if torque is constant, then your power is going to be directly proportional to speed. Now this is going to be less than the rated speed, and this is we are calling as armature voltage control. The armature voltage control comes under the category of constant torque and variable power drive. Similarly, if you go for the speed above the rated speed, you are going for constant power and variable torque drive. Variable torque drive. This is going to be constant power and this is going to be torque. For example, if power is going to be constant, we have just seen power you can write as torque multiplied by speed. So if power is going to be constant, torque is going to be inversely proportional to the speed. Is it clear for everyone? All the candidates who are watching me, just quickly confirm whether you are getting my point clearly or not, and quickly like the session if you have not liked till now. So first we will be starting with the field flux control. First we will be starting with the field flux control. When we talk about the field flux control, you have to understand that it gives above the rated speed control. If you want to control the speed above the base speed, then you are going to use the field flux method. Now we will see this method for the shunt motor and the series motor separately. For example, let us start with the shunt motor. Suppose you have a shunt motor. We will be starting with the shunt motor. Now there is nothing to remember, nothing to mug up, everything is logic. Please try to understand. First we will write, suppose this is your shunt motor. This is your shunt motor. This is your shunt motor. Now this is your shunt field, this is your armature, this is the supply voltage because it is a motor, this is going to be line current, this is going to be armature current, shunt field winding current. If you want to control the flux, so what you will do? You will put some external resistance. Suppose it is a variable resistance in the field circuit and you are going to vary it. Yes or no? Now let us try to understand. Suppose case 1 you are saying when R rheostat is 0. When R rheostat is 0, the flux is going to be directly proportional to the shunt field current. Shunt field current for the DC shunt motor is going to be V divided by RSH. Are you getting this or not? Clear? Now suppose for this flux, this shunt field current, you are getting the speed N1 and we are assuming that this is the rated speed. We are assuming that this is the rated speed. Now let us take case 2. Case 2, when this rheostat or the variable resistance is non-zero. When it is going to be non-zero, it means it is going to reduce the field current. If it is going to reduce the field current, definitely the flux is also going to be reduced. Now your flux is again directly proportional to the shunt field, which is given as V upon RSH plus RH. So definitely you can understand that field flux is going to be reduced. Yes or no? So if you are calling this as phi 1 and this is as phi 2, then 100% if this is non-zero, then you can say that phi 2 is going to be less than phi 1. Now the real story begins from here. You know that the back EMF is directly proportional to flux and speed. And you are saying that by putting the external resistance, the shunt field flux has reduced. Now if the shunt field flux has reduced, you please try to understand the speed belongs to the mechanical system, does not change suddenly. because it is a mechanical system. Speed is related to the mechanical system and it has some inertia. It cannot change suddenly. So if the flux is reducing, what is the first consequence? The first consequence is back EMF is going to be reduced. How many candidates are able to understand this? Just tell me yes or no. Are you able to understand this or not? That the first consequence of reducing the flux is back EMF is reducing. If the back EMF is reducing, what is going to happen with the armature current? What is armature current? V minus EB upon RA. Now this V you have not disturbed, EB you have reduced, RA is not disturbed. So if EB is reduced, you know that armature current is going to be increased. Now if you write about the torque you are defining as phi into Ia. Now I am saying, and you please understand this, the change or the reduction in the flux is small, whereas the increase or the change in armature current is more, so the torque is going to be increased. So the torque is going to be increased, and if the torque is going to be increased, finally the speed is going to be increased. This is the whole story. If you are able to understand this, then a lot of problems you can easily solve. Let me just repeat what is the consequence. Initially rheostat resistance was 0, so you are getting phi 1 flux and you are getting N1 speed. For the second case, when the rheostat resistance is not 0 in the field circuit, flux in the field winding is going to be reduced. When the flux is reduced, you are saying back EMF is going to be reduced because the speed cannot change suddenly. If the back EMF is reduced, the armature current increasing, flux reducing. But this is the most important step, that armature current increasing and the flux reducing. So the total effect is torque is increasing. Torque increasing means speed is increasing. Now you have to understand why you are having the reduction in flux small and the change in current large. If you draw the magnetization curve, in general I am saying, if you draw the magnetization curve, it is going to be saturated after some time. And generally you are operating your machine very close to the saturation point because you want the maximum flux, maximum torque, maximum EMF. Now what is happening, if you see near the saturation point, you can easily observe for a magnetization circuit, the change in current is going to be large, whereas the change in flux is going to be comparatively less. Are you getting this or not? Everybody just tell me yes or no. Are you getting this? Legacy ji, how are you? Are you getting this? Now we have reduced the flux. Suppose you want to increase the flux. And you want to control the speed below the rated speed or base speed. For below the rated speed, field flux control is not used. Why it is not used? Can you tell me why it is not used? Because if you are increasing the flux, what is going to happen? Flux increasing means flux density increasing. Flux density increasing means core losses are going to be increased. Core losses increased means efficiency going to be reduced. Also, this method is going to be a non-linear control. Why it is going to be non-linear control? Because when you are increasing the flux, you know that the magnetization curve has the saturation point. That is why it is going to be non-linear. So this is the reason for the field flux control we do not use below the rated speed. Field flux control method is not used. Are you getting this idea clear in your mind? Everybody just tell me yes or no. Sukanya Banala. Yes. Now let us talk about the series motor. Let us talk about the series motor. Now in the series motor, if you want to do the speed control by using the field flux method, then my friend, there are three methods. There are three methods with the help of which you can control the speed. Number one is diverter method. Second method is field tapping. Third method is series and parallel combination. Series and parallel combination of field winding. Now let us try to understand first the diverter method. Diverter method, as the name indicates, you want to divert the current in the field winding. Diverter method. How you are going to divert the current in the field winding? Suppose this is your series motor, this is armature resistance, and this is your series field. This is your series field. This is the supply voltage. Suppose this is the back EMF, armature resistance. If it is a motor, this is going to be line current. This is going to be the series field winding current, and this is going to be series resistance. Now, if you want to reduce the current which is passing through the series field, what you are going to do, you want to apply a small resistance across this, which we are calling as RD, that is the diverter resistance. Now this diverter resistance will bypass some of the line current like ID. Are you getting this idea clear in your mind? Tell me yes or no. Are you getting this? Tell me yes or no. How we are doing this? Yes or no? And this is going to be your armature current. This is going to be your armature current. Now one thing that you can write, that if you want to find the series field current, do you have any formula? Yes. If this is the line current and you want to find the current in this parallel path, so you will write RD upon RD plus RSE. RD upon RD plus RSE. Now you can very well understand that this RD upon RD plus RSE, this is going to be less than 1. If this is going to be less than 1, initially when this diverter resistance was not present, all the line current was passing through the series field winding. So initially, without this diverter resistance, the series field winding current was equal to the line current. But when you have included the diverter resistance, the series field winding current has now become less than the first case. If the series field winding current has reduced, definitely you can say the flux has reduced, and if the flux has reduced, you know that speed you are seeing is back EMF upon flux. In general, you can say if flux is reduced, speed is increased. This is how your diverter method is going to work. Everybody just tell me, are you getting this clear in your mind or not? Yes, everybody tell me. All the candidates who are watching me, do not forget to like, share and subscribe the session. Subscribe the channel if you have not subscribed, and like the session. Are you getting this? If more and more candidates are there, I will also be motivated and I will be able to give my best. The second method that we want to see is field tappings. What is field tappings? Again, suppose this is your series field, okay, and now suppose your series field is going to have number of tappings. number of tappings. This is your supply voltage. This is the line current taken from the supply. This is your series field. This is armature. This is armature current. And these are the tappings available at the series field. Suppose this is 1, 2, 3, 4, 5 and so on. Now depending upon to which terminal you are going to connect, the number of turns of the field winding are going to be connected to the circuit, and you will be having ampere turns of the series field. They are going to be directly proportional to the number of, if n, or better write it T, if you have any confusion with n, T, that is the number of turns of series field winding. And you know that the series field flux is also going to be directly proportional to the ampere turns of the series field winding. So if the number of turns are increased in terms of the tapping, or you can say if it is reduced, the flux is going to be reduced. And again, if the flux is reduced, you know that the speed directly proportional to the back EMF upon flux. Flux reduced means speed is going to increase. Flux reduced means speed is going to increase. Everybody just tell me, are you getting this or not? Vignesh, Wiki. But are you getting my point clear in your mind? If you have any doubt, you can ask me. Clear? The next method is series parallel combination of the field winding. What is that? Again, suppose this is your series motor armature resistance. Now what we are going to do, have you ever eaten that Kit Kat chocolate? You know Kit Kat chocolate? So what I am going to do, this series field, suppose number of turns are TSE, this I am going to divide into two parts. This I am going to divide into two parts. Now I am going to connect it either in series or the parallel, and we will be getting the speed control. For example, suppose first I am going to connect it in series. First you are going to connect it in the series. So it is going to be like this. This is your supply terminal. This is supply voltage. This is TSE by 2. This is TSE by 2. This is the line current. This is the series field current, and this is the armature current, armature resistance. Everybody just tell me, are you getting this idea clear in your mind? Can you tell me what is the ampere turns of the series field winding? Ampere turn means current in each turn and number of turns. So what is the current? Can you tell me? What is the current? Can you tell me? This is the same current as armature current, series field winding current, and the line current. So I am writing IA TSE by 2. This is for half of the series field winding plus IA TSE by 2, half of this. So total you can say it is going to be IA TSE. IA TSE. Clear? Vignesh, Legacy, lot of new candidates say this is equation number 1. Now suppose I am going to connect them in the parallel. Now suppose I am going to connect them in the parallel like this. Now one thing you have to understand, during this serial and parallel combination, you are not changing the power taken from the supply voltage and the current you are assuming same. Again this is armature current, again this is armature resistance, this is TSE by 2, number of turns TSE by 2, this is going to be divided as IA by 2 and IA by 2 because IL is equal to IA. Now can you tell me what is going to be the ampere turns for the parallel combination? For the parallel combination it is going to be IA by 2 into TSE by 2 plus IA by 2 TSE by 2. Total it is going to be IATSE by 2. Say this is equation number 2. Everybody just tell me, are you getting this clear in your mind? If you have the series and parallel combination, yes or no? Clear? Now you tell me that if you want to compare the speed, suppose this is for the parallel combination and this is for the series combination, and you know that speed is going to be inversely proportional to flux. So can I write it like flux series upon flux parallel? Now flux is going to be directly proportional to the ampere turn. Now what are the ampere turns for the series? The ampere turns for the series we have found here, IATSE. This is going to be IATSE. What is phi P? Phi P is going to be ampere turns of the parallel combination. So it is IATSE by 2. This is IATSE by 2. So you will be getting 2. So you can say in case of parallel combination, the speed is going to be 2 times, that is the series combination. That is the series combination. But the most important thing is, when you are dealing with this, you have assumed that the power taken from the supply is going to be constant. So it is going to be a constant power variable torque drive. Constant power variable torque drive. All the candidates answer 2. Yes, great, Sukanya. Everybody just tell me, are you getting this or not? Now suppose I want to see if the same method I am using for the constant torque and variable power, what is going to happen. Suppose you are using it for the constant torque variable power. Variable power means voltage you are not changing, but suppose current you are changing. Voltage you are not changing, suppose current you are changing. So what is going to happen? If T2 is equal to T1, if T2 is equal to T1, what is, or better write it as parallel combination and series combination. This is torque for the parallel combination and this is torque for the series combination. You know that the torque of a DC motor is going to be directly proportional to the flux and the armature current. Flux is also changing because ampere turns are changing and current is also changing. That is why you are saying variable power. So it is going to be phi P IA2 and this is going to be phi SE IA1. Now phi P is going to be directly proportional to the ampere turns. Ampere turns for the parallel combination are IA2 TSE by 2. Yes or no? For the parallel combination, what is the ampere turns? IATSE by 2. But you are saying that the armature current is changing, so it will become IA2 TSE by 2. IA2 TSE by 2 into IA2. What is phi series? Phi series is going to be IA1 TSE and this is same and this is going to be IA1. Now TSE are going to be cancelled and you can write IA2 square is equal to 2 IA1 square, or you can write that IA2 is going to be root 2 times IA1. It means if you are going for a constant torque and variable power, then the current for the parallel combination you are getting root 2 times. Now again, if you want to compare the speed for the parallel combination and the series combination, again it is going to be phi series, phi parallel. It is going to be ampere turns for the series combination, ampere turns for the parallel combination. What is the ampere turns for the series combination? It is IA1 TSE And what is ampere turns for the parallel combination? It is IA2 TSE by 2. Now TSE again cancel, and you know that IA1, this 2 will go upside, and IA2 you can write as root 2 IA1. IA1 cancelled, you will be getting root 2. It means for the parallel combination, the speed you are getting is N SE, or series combination speed, multiplied by root 2 times. Now this is the reason why we are not preferring this constant torque variable power mode, because you can see the current is increasing. If the current is increasing, the losses are going to be increased. Current is increasing, so losses increase, efficiency reduce. At the same time, the speed increase is not significant. Not significant. For the constant power variable torque, the speed which you were getting was 2 times the series combination. But now what you are getting is only root 2 times. Everybody just tell me, are you getting this idea clear in your mind? Everybody just tell me, are you getting this clear in your mind or not? Yes? Clear? Okay. So now less time is there, but let us try whatever we can do, that we will do. Armature resistance control. Armature resistance control, first we will see for the series, for the shunt motor. For the shunt motor, armature resistance if you want to control, so simply what you will do, you will put some external resistance into the armature circuit. This is what you are going to do. What else you can do? So if it is a shunt motor, you have to put some external resistance. How you are going to put it? This is going to be your armature resistance. This is the external resistance you are going to put. This is going to be your shunt field. This is going to be your terminal. This is your terminal voltage, line current, armature resistance, external resistance which you have put, and this is shunt field winding current, and this is shunt field winding current. Now let us take the first case. First case, you are saying when external resistance was 0. When external resistance was 0, you know the speed N1 is directly proportional to back EMF divided by flux. Now flux this time, if you see, is going to be constant. Flux this time, if you see, is going to be constant. And how you can write the back EMF? Back EMF you can write as V minus IA RA. V minus IA RA. Where N1 we are assuming as the rated speed. Are you getting this? Now let us take the second case. Second case, you are assuming when RE is not equal to 0. When RE is not equal to 0, suppose you are having the speed N2, and this speed N2 is going to be back EMF upon flux. Again, suppose you are saying flux is constant because it is a shunt motor. Now this back EMF again you can write as V minus IA RA plus R external divided by flux. Flux constant, so better you can write it as V minus IA RA plus RE. Now if RE you are increasing in the circuit, definitely you can say the speed is going to reduce. The speed is going to reduce. Now listen very carefully, what are the consequences of this? What is back EMF? Back EMF is directly proportional to flux and the speed. This is almost constant, or you can say constant. Now, if the speed is going to reduce, back EMF is going to reduce. Speed is going to reduce, back EMF is going to reduce. And if you see the armature current, how you can write the armature current? V minus EB upon RA plus RE. Now, if you see, if back EMF is reducing, it means this total is going to be increasing, and if you are increasing the external resistance in the armature circuit, so this value is also increasing. So you are saying armature current is almost constant. Very, very important conclusion. This can be asked in your gate examination in terms of multiple select questions. Everybody just tell me, are you getting this idea clear in your mind or not? Listen, listen, listen. You remember this? Arise, awake, and stop not till the class is running. I can see some of the candidates, they are sleeping. Don't sleep. What is happening to the torque? Almost constant. Armature current almost constant. It means torque is constant. It means this method you are going to use for constant torque, variable power drive. Constant torque, variable power drive. Everybody just tell me, are you getting this clear in your mind? Are you getting this or not? Now friends, what we have completed, now for the series field, you have to see, and one method remaining is armature voltage control. This you can see on your own. I think I have given you enough logic so that you can understand the process, and it will take not more than 10 minutes to revise the remaining portion in the speed control. If you have this kind of understanding, you will not find any difficulty in the problems which are going to come in the gate examination. We are running short of time, so please allow me to just conclude the session. But before that, do not forget a very, very important information for all of you. Till 30th of January, we have opened that you can enroll in the Gear Up and Rank Up courses. Now this is the last opportunity if you want to enhance your performance in the gate examination, because Gear Up will give you a kind of quick revision for your theory, and Rank Up will give you a quick revision or practice for your problems. Now if you come to the 2022 vision, we are going to cover theory, numerical, and everything under the electrical engineering. 850 hours of live classes, 8,000 plus practice questions, 100 plus mock test, 120 plus chapter wise study notes. You can understand the enormity and the exhaustiveness of this particular course. Everybody just give me confidence whether the remaining 10% portion you can do yourself or not. You have to give me this confidence. Yes? Sukanya, Bignesh, Legacy, Shambhu, Chandar, Akumi, Tanish, everyone. These are the star faculties of electrical department who are going to mentor you for your coming preparation cycle. You must be knowing them. All of them are highly experienced and expertised in their field, and this is the result we have produced over the years. And my friend, 2020 has been a landslide where the Gradeup students have embarked upon, and they have made 60 plus selections in the top 100 rank, within top 100 rank. Now, last but not the least, Gradeup Super. As I have already told you, one subscription will give you access to all the structured live courses on the Gradeup platform, and you can also access all the online mock tests as per the green card given by Gradeup. For any further clarification, you can contact this number. Yes, legacy free mock test is also available. Everything is free on Gradeup. Everything is free on Gradeup, but there is a condition. For getting everything free on Gradeup for your preparation, you must subscribe to Gradeup Super. Gradeup Super, you must subscribe. Rest, everything is going to be free of cost. So friends, thank you so much for joining me in this session. Let me again remind you about the session. 9 p.m. tomorrow, I will be discussing the testing of DC machine. Tomorrow, I will be discussing the testing of DC machine. Important topic. Do not forget to join me. Thank you so much for your time. Take care of yourself. Prep smart, score better. Go Gradeup. Thank you so much. Thank you. Thank you, everyone. Thank you. Take care. Take care. Keep rocking. Keep preparing. And go for the Gradeup. Go for the GATE 2021. Thank you so much. Thank you.